Hello everyone, our paper is titled as Robustness Evaluation in Hand Pose Estimation Model using Metamorphic Testing. I am Mushin and will present our work. Hand pose estimation is the process of predicting and describing hand pose in a given image or video frame. In general, hand pose estimation is a technique that captures a set of coordinates for specific joints known as key points that can describe a hand pose. It involves two main components, hand segmentation and hand landmark localization. Hand segmentation is the separation of hand from an image or video frame, whereas hand landmark localization involves identifying specific points on the hand and mapping them to corresponding hand pose parameters. As comparing to wearable-based hand pose estimation, vision-based hand pose estimation can provide more natural human-machine communication and facilitate many promising applications, which has led to a growing interest and attention towards it among researchers in the computer vision community. It's still early days for hand pose estimation models. These models are normally trained and tested on fragmented datasets, which may not reflect the wide range of real operations, so the ability of them to handle unfamiliar domains may be insufficient due to domain distribution disparities, meaning that more source and target data are gathered from the same probability distribution. Additionally, the performance of hand pose estimation models in controlled operating environments has not been truly investigated in the existing literature due to the lack of test oracle. The existing literature has found that the performance and robustness of hand pose estimation models suffer from occlusion, illumination variation, and rapid hand movement, which are three of major difficulties that existing hand pose estimation models normally face, and however, they are very common in practice. When HPE model estimate hand poses captured in a lab or under controlled environments, they usually perform well. However, the real-world environment is complex and a variety of uncertainties may occur, limiting the performance of HPE models. To evaluate the robustness of HPE models when confronted with such problems, it's necessary to subject them to various types of noise that can mimic real-world operating environments. Hence, our research questions in this work are: first, how would the model perform in situations where the testing images are not in ideal conditions? How is the reliability or robustness of the selected HPE models? How can we provide suggestions on the choice of HPE models for different applications based on the strengths and the vulnerability? While for the robustness testing process, metamorphic testing is chosen specifically, since hand pose estimation is among the popular beneficial machine learning models invented. They remain challenging in testing due to the black box nature of its core network. They are unsupervised with no explicit input and output specification. All we have are images of hands. This makes it hard to access the oracle information in the form of ground truth. Empty serves as an efficient approach to help relieving the potential vulnerability of hand pose estimation models. This could help us assess the model from various perspectives to ensure its consistency, stability, and generality. Compared to image classification and object detection, research on evaluating pose estimation model is limited. Cascade pose regression has shown that, unlike human allocators, algorithms have bimodal distribution of normalized distance between a part of detection and the ground truth, indicating multiple error modes, benchmarking, and error diagnosis in multi-instance pose estimation have introduced a method to analyze errors and a benchmark to compare different algorithms. However, to the best of our knowledge, existing works have not been evaluated true on the scenario signal that could potentially affect the HPE model's performance. Metamorphic testing has been used to detect faults in various domains and has been integrated with software analysis and testing. It has been a mainstream approach to handle Oracle problems in software engineering and used for quality assessment to detect real-world faults in learning-based systems. In our work, we have chosen to focus in a few of the state-of-art models, namely media pipelines, body hands plus OpenPose, and NSRM hand. These models exhibit high performance, achieving an average precision score of over 90% under controlled conditions. The selected models employ a hand number consist of 21 key points to describe target hand pose. To verify the reliability of our experiments, we have computed various evaluation metrics. We have selected intersection of union to measure the degree of overlap between two sets of data, which is a widely accepted method to evaluate object detection and segmentation tasks. A threshold of IOU equal to 0.5 has been set to differentiate between true and false prediction outcomes. Additionally, we are using Euclidean distance to measure the distance between the predicted and the ground truth points with a threshold of 10 mm, which is the average threshold used in the Ferrari-Ham dataset. Using these two metrics, we can calculate the confusion matrix for each test result. Positive outcomes indicate that the models provide predictions, while negative outcomes suggest that the absence of predictions. Each prediction is classified as true or false, indicate whether it is correct or incorrect prediction. Since all testing images contains one hand, there are no negative test cases leading to a true negative outcome. False negative occur when the models fail to make any predictions. The positive outcomes are measured using the defined threshold value for IOU and Euclidean distance as shown in the table. From the confusion matrix, we derive the precision, recall, and FE score. This matrix evaluates the result based on the quality, quantity, and the harmonic mean of the two. In this study, we utilized two OpenPose datasets, namely Ferrari-Ham and CMU panoptic hand, which consist of real captured images with various hand poses associated with their key points coordinate annotations. To ensure fair comparison, we selected a subset of data from each dataset for testing purpose and classified the data into two groups, hand with and without objects. We used 2,500 sample images with objects and 3,000 sample images without objects for each dataset. For the Ferrari-Ham dataset, we did not resize or crop any images because they all feature a single hand and have a standard size of 244 times 244 pixels. For the panoptic dataset, Chen et al. Previously cropped the images to a square patch that is 2.2 times the largest dimension of the boundary box, encompassing all hand key points. We then resize these images from panoptic dataset to match the size of the Ferrari-Ham dataset. Initially, we used both datasets as our source test cases and applying the metamorphic transformation only to images without objects to ensure a reliable evaluation. Before verifying any metamorphic relations, we classify the original dataset into two categories based on whether hands are presented with or without objects. We then conduct our experiments by testing the pre-trained models on this classified dataset to obtain a reliable baseline. Upon comparing the two tables above, it is observed that the result obtained from the panoptic dataset exhibit a more dramatic decrease as compared to those obtained from the Ferrari-Ham dataset. This decline could be attributed to various factors, including rapid hand movements, variation of illumination, occlusions, and information loss during image resizing or cropping. We now present our experiments to verify our metamorphic relations. The first metamorphic relation was built to investigate the relation between occlusions and the performance of HPE models. We aim to observe a strong correlation between the performance of HPE models and the number of occluded kin points on the target hands. This is because kin points on hands are susceptible to occlusion or self-occlusion due to all-object interactions. We derived test case TC from our MR1, which contains 21 subgroups with the number of occluded kin points increasing with the level of occlusion. Samples of testing images from different occlusion levels are shown at right. Regarding MR1, the test results for both datasets are presented here. However, the obtained result did not align with our initial hypothesis for MR1. From the presented graphs, it is evident that the performance degradation of HPE models does not have strong correlation with the number of occluded kin points. The degradation levels vary significantly based on the occluded kin points, which indicate that some kin points have more significance in hand pose estimation than others. Our experiments with media pipe hand, body hands plus open pose model shown that the recall and F1 score decreased sharply at 4 crucial points, marked by the vertical dot lines at occlusion levels 5, 9, 13, and 17 when specific fingers were occluded. Meanwhile, NSRM hand showed a slightly stronger correlation between the overall performance and occlusion level, suggesting that the model is less inconsistent with MR1. So how these models respond to hands with occlusion apply on the individual finger? To explore this, we derived our second metamorphic relation, which was introduced to help evaluate the vulnerability of these models to finger occlusion. We expect the performance of HPE model should not be degraded by the introduction of slight occlusion on hand region that are prone to be occluded, such as particular finger, in line with the MS-COCO 2017 validation dataset, which used 17 kin points to annotate a body pose and classify pose with 1 to 2 occlusion kin points as slightly occluded. We refer to slightly occlusion in our study as introduction of 4 occluded kin points, given that the selected model used 24 kin points to annotate a hand pose. Testing images with different types of finger occlusions are displayed on the right. Based on the assumption of our second metamorphic relation MR2, we expect to observe robust performance from these models when dealing with finger occlusion. However, the results shown here are inconsistent with MR2, as the performance degradation of the model varies when different fingers are occluded. Observing the result, it can be seen that applying occlusion on the thumb finger generally causes this model to perform less precisely than when applying occlusion on other fingers. The recall value dropped by roughly 20% for media pipe hands on furring hand and around 40% for media pipe hands on optic dataset, and for body hands plus open pose on both datasets from their respective baseline. The worst precision value were observed from the result of the NSRM hand, which different from the precision value of media pipe hands and body hands plus open pose, which consistently hovered above 75%. Therefore, it can be found that applying occlusions on the thumb finger only will greatly transform the shape of hands, leading to a significant performance degradation of these models. From MR1 and MR2, we get to know how serious the impact of occlusion on this model's performance was. In real life, the changes in visibility by illumination variation are also unavoidable. So how this model responds to illumination variation? This leads us to develop our third metamorphic relation, MR3, which aims to evaluate the model's robustness against uncontrolled lighting conditions. Our expectation is that the performance of HPE model should not be degraded if the exposure rate of the original images is altered to mimic the illumination of different operating environments. Sample testing images are present on the right. However, this model accepts varying levels of performance deviation under the 4 illumination variation test cases, with strong underexposure and strong overexposure having the most significant impact on their performance. On average, an SRM hand forced to correctly estimate over half of underexposure hands from TC7, while body hands plus open post experiments a decrease in recall value of over 39% on TC10. One interesting finding is that media pipe hands demonstrate relatively robust performance when tested with test case generated from the foreign hand dataset, suggesting that the model may have been trained to handle relevant illumination variation, but may not have sufficient experiments to deal with all types of illumination variation used for our experiments. Based on our findings, we have reason to believe that these models are not adept at handling illumination variations and may not perform optimally for strongly underexposed or overexposed hands. In addition to occlusion and illumination variation, motion blur resulting from fast hand movement is a common occurrence during gesturing or object interaction. To further evaluate the robustness of HPE models in handling uncontrolled conditions, we introduce our 4 metamorphic relation, MR4. We expect that the performance of HPE model should not be degraded by the introduction of motion blur, which simulate real-world fast hand movement. Samples of testing images from test case 11, 12, and 13 are displayed on the right to showcase different degrees of motion blur. However, our findings show that none of these models demonstrate a robust performance against motion blur, which is inconsistent with our fourth metamorphic relation, MR4, as demonstrated in the graphs. Both media pipe hands and body hands plus open posts exhibit a similar decrease in precision compared to the baseline, although they both remain above 87%. However, their recall values differ significantly. The recall values of body hands plus open posts on each test case tend to fall below 50%, and the model is significantly impacted by the vertical and diagonal motion blur, leading a dramatic decrease in the number of identified hand poses and their corresponding key points. Media pipe hands perform better except for the result obtained from TC13, where diagonal motion blur still has the most significant effect on its performance. On the other hand, we can say an SRM hand shows the most stable performance when dealing with motion blur, comparing with other models. Despite that, the model shows slightly greater fluctuation in precision than recall due to its design to assume the involvement of a hand in any images. We have created a table summarizing the objects of each MR and how it was validated to its respective theses. To categorize our findings, we have created 3 categories: positive, negative, and recommendation. In terms of positive findings, both media pipe hands and body hands plus open posts demonstrate high precision, making them relatively suitable for applications such as gesture recognition or sign language recognition. Additionally, an SRM hand exhibits high sensitivity and stable performance to deal with motion blur, which may ensure its application in virtual or augmented reality under controlled indoor environments. However, both media pipe hands and body hands plus open posts perform poorly with diagonal motion blur. An SRM hand is more susceptible to illumination variations, particularly in dark environments. The poor performance of HPE model is mainly impacted by occlusions, illumination variations, and motion blurs, which not only degrade precision but also decrease the number of hands identified. Furthermore, existing HPE models are not robust against this constraint as well as adversarial attacks. Considering the rapid development in the field of pose estimation and with spore variations considered in the design stage of HPE models, we believe that these models can overcome the operating constraint caused by occlusions, illumination, and motion blur. In conclusion, we found that MET is a valuable tool for creating test cases that replicate various real-world variations as demonstrated by the set of MRs used in this study. The derived dataset based on these MRs allow for evaluating HPE models with a wider distribution of conditions. By analyzing the test case generated through MET, we were able to observe how occlusions, illumination variations, and motion blur affected the performance of the HPE models. Overall, MET proved to be effective for identifying illuminations and enabling researchers to evaluate models of black box nature in order to enhance their robustness and reliability. We have to admit that the metamorphic relations developed for this study may be too strict for current hand pose estimation methods and thus present an opportunity for further improvement. In future work, we could aim to identify more flexible and comprehensive MRs, as well as establish more rigorous thresholds with approximate values instead of exact values to aid evaluating the robustness of HPE models. We may also could investigate the impact of other constraints, including variation in viewpoints, scale, and background collector, with the goal of improving the robustness of HPE models in uncontrolled operating systems. Moreover, the potential of combining metamorphic testing with other evaluation methods, such as automatic testing, could be explored to enhance the robustness of HPE models. We have now concluded our presentation. Here is a list of references that we have used, and we would like to express our gratitude to all those who have listened to us. Thank you.